Okay, I think we'll get started. So, lecture 3, I think maybe the title is not quite what was announced on the program, but the idea is very much the same. So, very quick review of a couple of points that we've done in the first two lectures. We saw how to use, say, model comparison games and locality results to establish limits on the expressive power of first-order logic, and to some extent also monadic second-order logic. For instance, we showed that you could use the locality of first-order logic to show that connectivity is not doable in monadic existential second-order logic. For monadic second-order logic, we showed the connection between MSO and automata, yielding two significant results, of which I kind of gave a glimpse. The Buchy-Elgot-Trachtenberg theorem, which relates MSO to regular languages of strings, and Courcell's theorem, which basically gives a limit on the expressive power of MSO. You can think of it that way, or another way is it provides an efficient algorithm for evaluating MSO formulas on structures which effectively are decomposable, right? So the important property of MSO here is there are certain kinds of decompositions of structures where evaluating the MSO formula on the structure can be reduced recursively to evaluating it on its component parts. And tree decompositions provide the natural way of doing that, and that's the core of Courcell's theorem. So in today's lecture, I want to return to first-order logic and talk about the complexity of deciding. This is what Fauquion called the query evaluation problem. We have a finite structure A, and we have a formula phi, and we want to decide whether phi is true in A. And as Fauquion argued, that this can be done essentially in time. Well, given this thing has two parameters as input, structure and formula, this is exponential time in polynomial space. But breaking it down into its parameters, you can roughly say it is, if n is the size of the structure, it's the length of the formula times the size of the structure raised to the power of the nesting depth of the quantifiers. In fact, if you do it carefully, you can make this the number of variables that appear rather than the nesting depth. But this is good enough for our purposes. And the space required is m times log n, the number of quantifiers times log of the size of the structure. Essentially, you have one, if you will, pointer into the structure for every variable that appears, and the pointer requires log n bits to point to an element of the structure. So this problem is in polynomial space. This, as I said, is the query evaluation problem. I call it the satisfaction problem in the sense that this is the satisfaction relation. And so we're talking about the complexity of this binary relation, right, on finite objects. Often in the literature, this also goes under the name of the model checking problem for first order logic. So all of these mean the same thing. So the problem is in P space. But if you fix the formula phi to get what Fauquion called the data complexity for a fixed formula phi, the collection of structures that satisfy it is decidable in logarithmic space in polynomial time, right? That's just what this says. If L and M are constants, that's a polynomial, and that's a logarithmic function. So, but the problem as given with as a binary relation on two objects is in fact P-space complete, well, even for fixed A. So you can fix A and look at, to be a two-element structure even, and the collection of formulas phi that are true in it is P-space complete in general, because you code QBF as a special case. Okay. The title of this slide is first order contained in an initial segment of P. There's a title of a paper by Stolboishkin and Teislin that appeared, as you see, about 20 odd years ago. And the question they pose is it possible that there's a fixed C so that for any first order formula, the models of the formula are decidable in time n to the C? Right? This is what they mean by an initial segment of polynomial time. Could it be the case? And the answer is Well, if P equals P space, the answer is yes, right? For the simple reason that then the satisfaction relation itself, being in P space, is in polynomial time. And so, in particular, for any fixed formula, the class of structures that satisfy it is decidable in this time-bound n to the c for a fixed value of c. So, though we suspect the answer is no, it's going to be hard to prove, because to prove it's no, you have to separate P from P space. Okay? Now, this is the question as they posed it. A more uniform version of the question is, can you find a constant c and some computable function so that the satisfaction relation is in this sort of time? Okay? So rather than saying for each fixed formula is there an n to the c algorithm, what we really want is something that will translate formulas into n to the c algorithms, right, computably, and that would mean that the evaluation problem, the query evaluation problem, the satisfaction problem, is in that sort of complexity. Okay, so this is the more reasonable form of the question. Again, of course, we expect the answer to this in general is no, and I mean we can make the no answer a bit more solid than this thing over here in the framework of parameterized complexity. So this kind of complexity is what's called a problem with this kind of complexity is said to be fixed parameter tractable, right? Really, it's saying that for any fixed value, so this is complexity expressed in terms of two parameters L and N, C is a constant, and it's saying if you fix the parameter L, this is tractable, but in a sort of effective computable sense, rather than in this sense. Okay, so this is what we call the class FPT, problem solvable in this way. Now, I assume not everybody here knows about the framework of parameterized complexity. There's a whole slew of complexity classes. I mean, the idea is, you know, classically we define complexity classes like P and NP and so on, all by measuring complexity in terms of one parameter, the size of the input. Parameterized complexity is, well, what about if we consider the input to be multidimensional? It has several parameters. You want to express the complexity in terms of several parameters, but we want something akin to the lower bounds methods we have of complexity theory of NP completeness, and etc. So we have to define complexity classes somewhat differently. And in this context, FPT is considered the sort of the tractable case. So if you have an input which is expressed in terms of two parameters, we don't really care about the dependence of the parameter L, as long as for fixed values of L, it's tractable. And tractable here means polynomial time, and the exponent itself doesn't depend upon L. Okay, that's the important thing. So that's what we call FPT. And then there's a hierarchy of what are considered intractable complexity classes. I'm not going to run through the definitions of these. Okay, and there's sort of complete problems at each level of the hierarchy. There's this thing that sits on top called AW star. And it turns out that you can show that the satisfaction relation for first order logic is in AW star complete. So it's very unlikely that it's going to be an FPT. Okay, so this kind of puts this in a solid basis. But what I want to do in this talk is talk about restricting the class of structures, particularly through notions of sparsity, and finding classes of structures where this evaluation problem, the satisfaction relation, turns out to be FPT. So in some sense, okay, yeah, this is a good point to illustrate this. So we're looking at the satisfaction relation for first order logic. Now, people who define these parameterized complexity classes were often interested in graph problems. So let's look at a little bit at the definability of graph problems. A classic example is the vertex cover problem. Here it is, for a fixed value of k, I can write down a first order formula that says there is a vertex cover in the graph of size k, right? I've used this example before. There exist k elements, and then for every pair of elements which form an edge, one of the endpoints is in this set x1 to xk. That says there's a vertex cover. Now, vertex cover is the classical example of a problem which is FPT. in the sense that there is an algorithm that solves it, which is exponential in k and times a linear function of n. Okay, it's an NP-complete problem, but it can be solved tractably with a function which is though exponential in k, the dependence on n is linear. And notice, so here I'm writing down a formula which depends on k. So I'm translating the vertex cover problem into first order logic, and the translation takes the value k to a formula whose length is dependent on k. I can do the same for, say, independent set. I could have written clique, but there's a reason why I'm saying independent set. The independent set problem for a fixed value of k says there exist k elements, says that pairwise there's no edge between them. Right? There's an independent of set k, size k.
You want to say they are different.
Sorry?
In this case, you need to say they are different.
You're right. Yes. Yeah. And xi is different from xj. Right. So the independent set problem is W1 complete. So this already shows that the satisfaction relation for first order logic is W1 hard, right? Because this is a reduction which takes an independent set and for each value of k writes down a formula whose length depends on k, which is true in the graph if and only if there's an independent set. Dominating set is W2 complete, turns out, and I can, here's the first order formula, which says there's a dominating set of size k, says there exist k elements, and for every y, if y is not among the xk, then there's an edge from one of the xi's to y. Okay? Yes?
You mean completeness under polynomial time reduction?
Under FPT reductions, which is a more relaxed notion, right? Okay, so, and then, I mean, it's not hard to construct formulas which give you complete problems at every level of the W hierarchy, and as I said, the satisfaction problem turns out to be complete for this class AW star, which sits right at the top. Okay, so now what we want to say is, can we restrict the class of structures? One way to get a handle on this is restrict the class of structures and say, we're given a first order formula and a structure from this class C, yes?
Just for the sake of having an intuition, what W1 and W2 should be understood at an intuitive level. I mean, can we connect it to quantifier numbers?
Yes. I mean, this is quite right. I mean,
this is the definition of W.
Well, you can take it. I mean, it is. You can take it as formulas with you know, k existential quantifiers, and then close it under FPT reductions, and that's the class W1 pretty much, right?
You start with a clique problem, right?
You start with a clique. Yeah, exactly. I mean, the classic definition is just the closure of clique under FPT reductions, or closure of independent set. And then if you look in the Flum and Grohe's book on parameterized complexity, they give the definition very much in terms of a certain class of formulas you can write down, and then you close that under FPT reductions. Okay.
So somehow, for vertex cover, the formula you write down is not very edifying in terms of its setting within this.
That's right. That's right.
Okay.
Yeah, I mean, the naive way of writing the formula suggests this should be W2, right? But it turns out to be FPT. Okay. I mean, it would be interesting. I've never really thought about whether there's a syntactic explanation of why. You know, you can read off the formula for vertex cover why it's FPT, but.
I don't have a good description of complexity of the parameterized class. I think that's.
Well, yeah. I mean, the Flum and Grohe attempt some sort of thing, but it's.
Say that the clique, I mean, in some sense.
Yeah. Okay. So now I'm going to look at this question. Restrict the class of structures in a way to make, for some interesting classes, this problem becomes FPT. Okay? And in some sense, we've already seen this, because Courcell's theorem tells us that even for monadic second order logic, rather than first order logic, the evaluation problem, right, is as I said, for every fixed formula, there's a linear time algorithm on the class of graphs of tree width at most k. And since all the translations of the formula to the automaton, etc., are computable, it actually tells you that the satisfaction relation or the evaluation problem, when you restrict this to be the class of graphs of tree width at most k, and this problem is FPT, even for the wider class of formulas, taking MSO. Okay, and now in the rest of the lecture, I'm going to look at some other classes for which this is not true for MSO, but it turns out you can do it for first order logic, and essentially the methods rely on the locality of first order logic, right? The methods of proof. So there's going to be applications of locality in various ways. And the first one I'm going to look at is the class of graphs of bounded degree. So I write dk for those structures in which every element has at most k neighbors in the Geifman graph of A, right? Remember, the Geifman graph is just the thing which tells you two things are adjacent if they appear together in some relation in the structure. So, and this was proved by Seyse somewhere in, what, 1990, I guess, or in the 90s anyway. That for every sentence of first order logic and every k, there's a linear time algorithm deciding this. And I mean, the way I formulated here is non-uniform, right? It doesn't tell you that there is a single algorithm. And because the proof I'm going to, I mean, you can make it all effective and uniform and prove it's FPT, but I'm going to give you a sort of high-level proof which doesn't make that explicit. Note, this is not true for MSO unless P equals NP, in the sense that I think three colorability is already NP complete for graphs of degree bounded by 5, maybe even 4, but certainly 5, right? Graphs of degree 5, three colorability is NP complete. I can write down an MSO sentence which says that a graph is three colorable. If this was doable in linear time, then P equals NP clearly, okay? So we don't expect this to be true for MSO, right? Crucially, this is specifically about first order logic now. And the proof, as I said, is based on locality of first order logic. Says this proof.
So is this how you understand the theorem, or that for every k there is a linear?
For every phi and every k, there's a linear time algorithm which determines. So, okay, I mean, effectively, if you want the strong version, then it is a
because
phi.
With complexity, are you doing data complexity, or are you doing?
So this is really saying that the data complexity is linear, as stated. But you can say it more general, the more uniform version is that this can be decided in time. I really should say order of some function of k and the length of phi times the size of A, right? So it's linear in A with some computable function of k and the size of phi. But so if you fix k and phi, this is linear. That's what that's what that form says.
Can you tell us what that function is? Or
Let's see the proof, and the proof I'll show you gives you a horrendous function, okay? And yeah, so the proof is based on locality, and Seyse in particular used Hanf's theorem, and I'm going to give you that proof. There's in some sense an alternative based on Geifman's locality, which possibly gives you better bounds. And but just, I mean, I'm going to, at classes I'm going to look after this, we have to rely on Geifman's theorem. But as a sort of warm-up, I'll give you this one. So what's the argument? So I'm going to have to use the version of Hanf's theorem that Sam kind of alluded to when I gave the weak version, the one with thresholds. Okay. So remember, in a structure A, we have the neighborhood. I'm using a different notation for neighborhood, I suddenly realized. Anyway, my LaTeX macros are different in this file. Anyway, so the neighborhood, our neighborhood around an element A in the structure right, is the substructure of A generated by those elements at distance at most r. And before I defined the notion of Hanf equivalence up to radius r by saying there was a bijection between the structures, preserving isomorphism types of neighborhoods, which basically means for every isomorphism type, the numbers are the same on both sides. Now I want to weaken that requirement, saying I count the numbers only up to a certain threshold. So you count the number of isomorphism types of each neighborhood. They're the same on both sides, or they are bigger than this threshold q. Okay? So, as an example, right? My example application, right, if you remember the cycle and the two cycles, are Hanf equivalent with radius r. If radius r is sufficiently small compared to the length of the cycle, the neighborhoods look the same. And the sum of these two lengths is the same as this to get the bijection. Now that I've put this threshold q, if the size is big enough with respect to q, we don't care that the sizes of these two add up to the same, right? Because all neighborhoods look the same, actually. Every neighborhood is a simple path. And if there are enough of them, they're more than the threshold q, so these two are q equivalent, right? Okay. And the stronger version of Hanf's theorem is that this is already enough to get us p equivalence with respect to first order logic up to quantifier rank p, right? So for every p, we can find r and q for which this is true. Two structures which are RQ equivalent are P equivalent.
So R was 3 to the P.
Yes.
What is Q?
What is Q?
It should be something like P, right?
It should be, well, yeah, but it should be something like, yes. I'm trying to picture the game argument. It gets a bit tricky if the proof I usually think of for this goes via Geismann's theorem, and that doesn't give you a direct bound in terms of P. So I'll pass on that for the moment. You can prove this directly as a consequence of Geismann's theorem, which I mentioned earlier. Okay. Now I'm going to just say how we use this for the result I want about bounded degree graphs. So suppose, or bounded degree structures. Suppose A is in DK, has at most k neighbors. Then this gives us this bound on the size of neighborhoods. The R neighborhood around A has at most k to the R plus 1 elements, right? A has at most k neighbors. Each of those has at most further, at most k neighbors, and so on. You can do better than this. It's, you can do k times k minus 1 to the R. But anyway, you go on up to radius R, you get at most k to the R elements, and I put in the plus 1, I guess, for the element A itself. And therefore, there are up to isomorphism only finitely many such neighborhoods, right? There's a bounded size. There are finitely many isomorphism classes. We count these isomorphism classes only up to a certain threshold, and therefore there are only finitely many equivalence classes with respect to this, right? Note, if I didn't put that threshold, this isn't true. Because if I'm counting number of neighborhoods unboundedly, obviously I get infinitely many classes. And you can characterize each of these classes by a finite table, basically list all these isomorphism types, and for each one of them say the exact number, that should be Q, or say it's bigger than Q, if it is. Okay? That's a finite table describing this equivalence class completely. So now let's say, to evaluate the first order sentence. You start with the first order sentence. First of all, you just compute the set of tables describing all these classes, and for each one, you say whether phi is true in that class or not. Right? And this is what, just the fact that you can compute this requires proof. It doesn't follow directly from, the proof of Hanf's theorem, it requires work to show that this is computable from phi. And that's where this function is coming from, right? But this computation is independent of any structure. You construct this table beforehand, and now your linear time algorithm, so from k and phi you compute this, and now your linear time algorithm is given the structure. Look at each element of the structure, look at its R neighborhood, and determine its type. What isomorphism type it is. You construct the table describing the RQ. I've got these class of A, and then compare against the table to see whether it satisfies the formula phi. Okay. So this is kind of brute force. We've just enumerated everything that can happen with every collection of neighborhoods beforehand, and then the linear time algorithm just looks at all the neighborhoods. There are n of them, and checks.
Did you say deciding whether a class is consistent with formula?
Sorry, deciding?
How to decide?
Well, this is done beforehand, right? Whether the formula is consistent with each of these.
Yeah, I'm asking whether that's computable.
It is, but it's not at all obvious. Okay, that's okay.
To get this in linear time in A, you're making some assumptions about how A is represented or something like that. So everything has some sort of
About how.
in tabular form, but maybe it's each element has a pointer to all the things it's related.
That's right. Yes. Yes.
Otherwise it'd be quadratic or something.
That's right. That's happening. Which would still be FPT, but you're right. To get it linear, you have to assume some kind of adjacency list representation of the structure rather than.
So the FPT is from the uniform vector, right? From what you put there.
Yes. So FPT would follow from the uniform. So the statement of the theorem I gave didn't say FPT. It said for every fixed k and phi, there is a linear time algorithm, and that's.
If I may say, this gives a bad name to fixed parameter tractability. It's kind of nobody would run this kind of algorithm.
Right.
Better than what you can do for click.
But there's this sort of general principle that things that have polynomial time algorithms also often have feasible algorithms.
Right.
Quite this, whatever this is, doubly exponential time function f.
Oh, it's worse than that.
Is it worse than that?
Yeah, no, it is. It's
because you have to compute the set of tables too.
That's right. So this function f is still elementary in this case, in the bounded degree case, but it's something like, I think, 4-fold or 5-fold exponential. But okay. So now I'm going to. We looked at bounded tree width, but there are two. The dependence. I mentioned MSO, but even restricted to first order logic. So you have something like this. This function there is non-elementary in the case of bounded tree width. Right? So if you take k to be tree width rather than degree, you also have something like this, but then the function is non-elementary in the length of phi.
Is that a provable? Is that a lower bound?
It is a lower bound. In the sense, assuming FPT is different from W1 or something like that. Yes. So the next step, there's a sequence of results about extending the class of structures on which we can prove something like this. The next step, it was essentially by Freak and Groy looking for a common generalization of bounded degree and bounded tree width classes. Okay, for both of those we know this is FPT. And they proposed this thing of bounded local tree width. So what is local tree width? So take t to be any non-decreasing function on the numbers. And we define the class of graphs or class of structures of tree width t to be those structures where for every element, if you look at the R neighborhood around A, I wrote the Geisman graph, but I don't really, I do mean the Geisman graph of this R neighborhood of A, that has tree width at most t of R. So in other words, the neighborhoods, we now say, have bounded tree width. The actual tree width may be a function of the radius of the neighborhood, Okay? But there is a function which bounds the tree width of the neighborhood as a function of the radius. That's what they call bounded local tree width. Okay? So we say that a class has bounded local tree width if there is some function t which bounds this. Right? It bounds the tree width of every neighborhood. So clearly, if a class has bounded tree width, it has bounded local tree width bounded by a constant function. Right? You just take tr to be the constant function k. Tk is the class of graphs of tree width at most k. Class of graphs of bounded degree has bounded tree width simply because the size of the neighborhood is bounded and therefore the tree width is bounded. Right? So you can take tr to be k to the r plus 1. An example which isn't either of these but which shows in some sense why this is an interesting definition is the collection of planar graphs. Turns out has bounded local tree width. Okay, this is essentially due to Epstein, and which kind of motivated this definition in the first place. That if you look at a planar graph of radius r, then its tree width is at most 3 times r. Right? You can construct a tree decomposition. It's a rather clever construction. Okay. And then Freak and Grohe showed that if you have a class of bounded local tree width and any formula, then again, evaluation is FPT. In this case, they get a quadratic time algorithm for every fixed formula, right? And every fixed, once you fix the class. And I want to describe this result because there's a very neat application of Geifmann's locality, which we haven't seen so far. Okay, so first of all, the idea is the following. So you have a structure, A. Now, around any element, you look at the neighborhood of radius r. The value of r is going to come from this formula you're trying to evaluate. The formula every formula is local in some sense. You extract from it the radius of neighborhoods you're interested in. You look at the neighborhoods of radius r. Now, because this neighborhood has tree width bounded by tr, and we know that once you bound the tree width, you can evaluate first order formulas, you can determine the type of this neighborhood. Again, the value of p is going to come from the formula, right? It doesn't depend on the structure. Now, this is the difference. Hanf's theorem relies on isomorphism types of these, and there are infinitely many of those. Geifmann's theorem is based on the first order types of these neighborhoods, and those we can bound. Right? The number of types is bounded, and so that's why we need to use Geifmann's theorem. So, quick recall. Geifmann's theorem tells us that every first order sentence is equivalent to a Boolean combination of basic local sentences. And a basic local sentence is simply the assertion that there are S elements pairwise far apart from each other, so that R neighborhoods are disjoint, and in each R neighborhood some formula psi is true. Okay? So it's a Boolean combination of these. So again, it's not stated in the theorem, but implicit in the proof. From the formula, you can construct this Boolean combination effectively. Again, this is a highly complex operation, blows up the size of the formula enormously, but you can construct this. So in other words, to show that for a fixed formula there is a quadratic time algorithm, it's enough to show that for any basic local formula there's a quadratic time algorithm. Because you start with the formula, you construct the Boolean combination, and then for each one of them, you have to do it. Okay, so how do we evaluate a basic local formula, a basic local sentence in a structure A? Right, we want to say there are S elements, and this holds. As I said, for each element, you look at the neighborhood, and you determine whether this formula psi holds in that neighborhood, using the fact that this neighborhood has bounded tree width, and therefore we have a linear time algorithm that does this. Right? Let's say if this thing is satisfied, we call the vertex red. And now the point is we want to determine whether there exists a set of red vertices of size S which are far apart from each other, right? What I call, I should say R scattered, but anyway, the distance, pairwise distance to R from each other. The R neighborhoods are disjoint. This looks kind of difficult because this looks again like the independent set problem, which is, W1 hard. So how do we do this? we have a set of vertices that are red. We choose them one by one, and every time we choose a vertex, we remove from the structure its entire neighborhood of radius 2r. Okay, not r, but 2r here. So pick one, remove all of its neighbors up to distance 2r, find another red vertex, remove all of its neighbors up to distance 2r, etc. Okay? If this process continues for s steps, we're done. We found s vertices, which are pairwise far apart, and their neighborhood satisfies it. What if it stops? Well, if it stops, that means that for some u less than s, we have found u vertices, and every red vertex is within distance at most 2r from these. All right? Because we've run out of red vertices. So you take the 2r neighborhood of these u points, take the union. Now you have a substructure of bounded tree width. And within this, you have all your red vertices. And finding them is, again, evaluating a first order formula on a structure of bounded tree width. So you're done. Okay. Okay. Now, maybe this will. So, the story of first order evaluation on sparse graph classes kind of continues. We had bounded degree classes. And I'm not giving you all the whole story. We had bounded tree width. And a common generalization, which is bounded local tree width. Okay. The next result in the story, which I'm not really going to give you the proof, but I'll introduce mainly to introduce the terminology, had to do with graph classes defined by excluded minors. So again, I'm not going to assume you know much about graph minor theory, but a graph G is said to be a minor of a graph H if you can get G from H by repeated applications of the operations of deleting an edge, deleting a vertex, and all incident edges, and contracting an edge, where contracting an edge is basically this thing over here. I'm not going to define it more formally, right? But if you have two vertices with an edge between them, you replace them by a single vertex whose neighborhood is all the neighbors over here. Okay, so if you can get, starting with H, through a sequence of these operations, you get to G. We say G is a minor of H. A more formal definition is that a graph G is a minor of H if you can find a subgraph of H called H prime, right? Subset of the vertices, subset of the edges, and a map which takes, let's say, the vertices of H prime to the vertices of G, right? So that for every vertex of G, its inverse image is a connected subgraph of H prime, and for every edge of G, there is a edge between something that maps to U and something that maps to V. These preimages under this map M of the vertices of G are called the branch sets. Okay, I'll come back to that. I think this picture sort of illustrates the idea. It's saying that if a graph G, for example, the triangle is a minor of H, that's really saying we can find three connected graphs in H with edges between them, which is, of course, just the same as saying that H contains a cycle. Right? So that's the one picture illustration of graph minors. Now, the theory of graph minors is very rich, and I feel a bit embarrassed standing here saying it in front of distinguished graph theorists. But here are a few facts. I mean, possibly the most famous fact about graph minors is that planar graphs are characterized by exactly two excluded minors, right? A graph is planar if and only if it contains neither the 5-clique nor the biclique on two sets of 3 elements as a minor. Obviously, any subgraph of H is a minor of H. It's a transitive relation. It respects tree width. So if G is a minor of H, then the tree width of G is bounded by the tree width of H. So in particular, if the tree width of G is less than k minus 1, then it cannot contain the k-clique as a minor. So we say that a class of graphs excludes H as a minor if H is not a minor of any graph in G. All right, so this is the definition of excluded minor classes, right? C has excluded minors if there is some graph H which is excluded as a minor, right? Which of course is the same as saying there's some clique it excludes as a minor. So we can actually attach a natural number parameter to any excluded minor class, the size of the smallest clique it excludes. Okay. So for example, Tk is an excluded minor class. It excludes the class of graphs of tree width at most k, excludes the k plus 2 clique as a minor. Possibly the most famous result in this whole field is the Robertson-Seymour theorem, which says that the minor relation is well quasi-ordered. So basically, in any infinite collection of graphs, there exists a pair of graphs such that one is a minor of the other. Okay, so there are no infinite anti-chains in the graph-minor relation. An immediate corollary is that if you have a collection of class-closed undertaking minors, then there is a finite collection of excluded minors which characterizes that class. Okay, that's because obviously the collection of minor minimal graphs that are not in the class forms an anti-chain, and this tells us that anti-chain must be finite. Also, in the course of proving this, there's an algorithmic result which says that for fixed, I really should say, for fixed graph, no, this is correct. For fixed G, we can find a polynomial time algorithm which tests whether G is a minor of H. Right, runs polynomial time in the size of H. Sorry?
It's another FTP result.
Yes, though here it's not at all clear that this function is computable. Right? The dependence on G is, but.
Sorry, for the corollary, don't you need to qualify it so that the trivial case is, the class could be all graphs which
yes.
are closed under.
And then this is the empty set.
Oh, sorry. Okay.
Right. That's right, I think. Okay. So it follows that any class closed undertaking minors is polynomial time decidable because there is a finite collection of excluded minors that characterizes it. And so we have a finite table. And using this, you can test membership in the class by just testing for each one of those finitely many graphs, whether it's a minor. Okay. So let's write MK for the class of graphs, which excludes the k-clique as a minor. And the result of Flum and Grohe is that first order logic is fixed parameter tractable on this. I'm not going to tell you how it's done. Essentially, well, maybe I will say a few words. Essentially, this is a uses the graph structure theory of Robertson and Seymour to give a tree decomposition of graphs in MK into pieces which themselves have bounded local tree width. Okay, and then essentially, sort of, you use the decomposition theorems like with the automata to break it up into pieces of bounded local tree width, and then use this. Okay, but note this itself doesn't have bounded local tree width. No, sorry, what am I saying? That's right. Right. So in terms of this picture, it fits. There are classes of bounded degree, obviously, which don't. What do I want to say here? I think excluded minors. No, excluded minors doesn't generalize this. It generalizes this. This is what I'm trying to say. And it certainly is incomparable against that. Right. Okay. I think that's right. Okay. But this, there's a sequence of further results, which I'm not going to go on, about the evaluation of first-order logic. This culminated in this paper in 2015 by Groy, Kreutzer, and Siebert, showing that first-order logic is fixed parameter tractable on any nowhere dense class of graphs. And the nowhere dense class of graphs are a sort of natural limit. These methods all rely on the fact that these class of graphs are sparse. And exactly what this notion of sparsity is and what the limit is I think, is very nicely captured in the definition of nowhere dense classes, which is where I want to get to next. To introduce it, I want to first introduce the idea of a shallow minor. So we have a graph, say H is a minor of G. Right, this is just the recap of the definition. H is a minor of G. If there's a collection of disjoint connected subgraphs of G, one for each vertex of H, such that whenever there's an edge between two vertices of H, there's an edge between two vertices in these. These are what I call the branch sets. So it's just an alternative way of stating the definition I had before. These are the branch sets witnessing that H is in G. If we can choose the branch sets in such a way that in each branch set there's an element so that the whole branch set is contained within the R neighborhood of that element, we say that H is a minor at depth R of G. Okay, so the point is that H is a minor of G, and the branch sets, these connected components which witness it, each of them is a graph of radius at most R. Okay. So another way of saying this is in getting H as a minor of G, you perform edge deletions and vertex deletions and contractions, but you can see these contractions as contracting a connected subgraph. You're not contracting subgraphs of radius bigger than R in getting H. Okay, so H is a minor of G at a restricted depth, and this allows us to state succinctly the definition of nowhere dense classes, which is due to Jarek, Neshetrel, and Patrice Osona de Mendes. A class of graphs is nowhere dense if for any fixed value of R, we can find a graph HR which is not a minor at depth R of any graph in C. Right, so the class C may not exclude any minors in that every graph might appear as a minor somewhere in C, but as you do it, you must increase this radius R. Okay, if you fix the bound radius R, then you exclude some minor. If you fix the depth of this, okay. And the idea is it's called nowhere dense because it has some really nice properties. You can ignore this last bit at the moment. It has really nice properties which show that these graph classes are sparse in a sense. Okay, they're hereditarily sparse in that you take any you start with a class and you take subgraphs, you still have a sparse, or maybe you take a class and close it under subgraphs and it'll still be sparse in this sense. And they're a natural limit because of this absolutely lovely trichotomy theorem, which Jarek and Patrice proved, which can be stated like this. So say you have an infinite class of graphs. I associate with it the following parameter. Let CR be the collection of graphs you get as minors of graphs in C at depth R. Okay, so those graphs which you can get. This may be richer than C itself. Among those graphs in CR, take the number of edges in G, its log, divided by the number of vertices in G. Okay, so now note this is going to be somewhere between 0 and 2, because the number of edges is at most the square of the number of vertices. So this ratio is going to be somewhere between 0 and 2. And you take its lim sup as over all graphs. And then you take the limit of that as R goes to infinity. This is a parameter you associate with a graph class C, right? And its value is somewhere between 0 and 2. Well, what they prove is, in fact, it can take only this, for any class C, this can only take 3 possible values, 0, 1, or 2. Okay? And the nowhere dense classes are exactly those where it doesn't take value 2. Okay. So they're in a sense, the completely characterized as the classes where you cannot construct a dense class of graphs by this process of taking shallow minors. Okay. So, I mean, this, I think, gives some confidence that this is a natural limiting case of sparse graph classes.
Can you say something about what characterizes the 0 and 1?
Well, so 0 is really just the trivial cases. I mean, the edgeless graphs, right?
Sorry.
And so 1 is really the nowhere dense classes, other than the trivial edgeless case, right?
Well, it's lim soup, so there's some. Oh, okay, in the limit. Okay.
Yeah. Okay.
It can be minus infinity, right? If it is class of edgeless graphs.
Oh, I see. Yes.
But
Yeah. No, you're right. You're right. Okay. Okay. So now, as I said, this recent result of Grohe-Kreutzer-Siebert's shows that this first order satisfaction is fixed parameter tractable on any nowhere dense class. Okay. And so this generalizes all of these. Okay. And it's again, it's an intricate application of three things. You have Geismann's locality theorem, but it needs a certain adaptation, okay, a rather clever adaptation. An algorithmic result about sparse neighborhood covers, which I'm not going to go into because I sort of don't have time. And the fact that these nowhere dense classes have a certain property called quasi-wideness. And this, I think, is interesting, so I'll say a little bit more about it. Okay, because this notion of quasi-wideness came up in a different context of studying preservation theorems in finite model theory. So let me explain a little bit about the quasi-wideness, and then I'll close with one quick slide in which I'll say how it's put together to get this fixed parameter tractability result. So what is quasi-wideness?
before you go, may I ask, on the FPT result, before we saw it was linear for the bounded degree, quadratic.
Yeah.
What happens here?
This is better. I mean, so even the excluded minor I didn't tell you, but the Flume-Grohe paper actually gave something like n to the 5. But this improves on that. This basically says that you can get an algorithm which is n to the 1 plus epsilon for arbitrary small epsilon. So it's better than quadratic. Okay, it turns out. Okay. So what is a wide class? So let's say a set of vertices in a graph is R scattered if their pairwise distance is greater than 2R. In other words, the R neighborhoods are disjoint. Okay. So we say a class of graphs is wide if whenever you fix R and M, there is a bound so that any graph bigger than that will contain an R scattered set of size M. Okay? So in any large enough graph, you find lots of points that are far apart. The classic example is classes of graphs of bounded degree, and I think what, again, Jarek and Patrice showed is essentially this is the only class that, variations of this are really all you get as wide classes, right? But it's clear why the class of graphs of bounded degree for any fixed bound is wide, right? In any large enough graph, I mean, once you fix R and M, you can compute a bound n so that if you have more than n vertices, they must contain m vertices, all pairwise distance greater than R apart. A simple case of class of sparse graphs, which is not wide, is trees, because obviously I can construct trees of just depth 1, arbitrarily large, and everything is distance 2, so it's not a wide class. Okay? So trees are what we call almost wide. So a class of graphs is almost wide if there is a fixed bound S. Now, given R and M, then in any large enough graph in the class, we need to remove at most S elements to get an R scattered set of size M, right? So in a tree, in this tree, I can always remove the central element, and I only need to remove one to get a scattered set, right? Then everything is sort of distance infinity in this particular tree. And this is true of arbitrary trees. So why is this? Fix R and M. In any large enough tree, either I have a very long path, and on that path I can find a scattered set. I can choose points that are far apart from each other. So there's already a scattered set. If there isn't a long path, and the tree is very big, there must be a point of high branching. Just removing that one point will create a large scattered set. So I never need to remove more than one element to create a large scattered set. That's why we say trees are almost wide. Okay? So trees are almost wide. Now I'll tell you planar graphs are almost wide, and this is not at all obvious. It requires work. But I'll just state the claim. In planar graphs are wide, and the value of S is 3. 3, possibly even 2. I think 2. Okay. I'm trying to think of the proof. I think 2 works. And in fact, it works for any class of graphs with excluded minors. If you exclude the k-clique as a minor, then k minus 2 is sufficient. That's why I was saying 3, because planar graphs exclude 5-clique as a minor. But I think from the k3 you'll get 2. But okay. And this proof that any class with excluded minors is almost wide is well, it's appeared in various forms, but in our paper with Atsarias and Fokion on homomorphism preservation, there's, I think, good exposition of this. So this leads us to the third step, quasi-wide classes. So here, the key point was that S was a fixed parameter. We get quasi-wide by relaxing this further and letting S be a function of R. Okay? So now S is a function, and we say a class of graphs is quasi-wide with margin S. If for any R and M, and any large enough graph, we can find a set of vertices of size at most S of R, so that this, removing them, you get an R scattered set of size at least M. And this proof that any class with excluded minors is almost wide extends almost directly to showing that any nowhere dense class is quasi-wide. Okay? So any nowhere dense class is quasi-wide. And again, this Jarek and Patry show that this is essentially characterizes them in the sense that the nowhere dense classes are the only quasi-wide classes closed undertaking subgraphs. Okay. So this is closely related to nowhere denseness. And this quasi-wideness property is what Groh et al. Use to show that first order logic evaluation of first order formulas is FPT on nowhere dense classes. And I'll only give you a very rough exposition in the 2 minutes remaining. We want to evaluate a formula from this nowhere dense class. So we know this class is quasi-wide. From this formula phi, we calculate the radius of neighborhoods we're interested in, which we get from Geifmann's theorem. In fact, we may assume that this formula is a basic local sentence to start with, so the radius is given. We identify a bottleneck set S. This is a set of vertices, removing which will create a large scattered set. In the graph you get by removing these, you color the remaining vertices with colors indicating how they were connected to the vertices in S. Right? You've removed S, but you want to remember how it was connected to the rest of it. You do that by attaching labels or colors to the remaining vertices. And then you can convert the formula phi to one that talks about these. Okay? Now, in this graph, we have this large scattered set and its neighborhoods are all disjoint. And we want to recursively use this algorithm to evaluate the types, to determine the types of the neighborhoods. So what worked in the case of when I showed you the proof for bounded local tree width was that once we looked at the neighborhoods, we knew that things were tractable because they had bounded tree width. Here we don't have anything like that. All we know is, these neighborhoods themselves belong to this class C, which is nowhere dense. And so we have to recursively carry on this process. The trouble is that because when you do this, you're changing the formula by putting in these additional colors, this will only work if the depth of recursion is bounded by a constant, right? Otherwise, the formula length becomes a function of the size of the graph, and your whole fixed parameter tractability will break down. So you have to make sure that the formula length doesn't blow up too much. And this was sort of the main obstacle to doing this. And then, okay, so the idea is, because you have this large scattered set, you're bound to find certain neighborhoods of the same type. You can remove them from the graph, and you get a smaller graph, and you carry on the recursion. So now the key element here, and I don't really have time to explain this, is to get this bound, though they're unable to bound this recursion by a constant. Instead, what they do is they produce a refined version of Geismann's theorem, where the quantifier rank doesn't blow up if you count these, let me go back, in a basic local sentence. Oh, it was far, okay, a basic local sentence, I'll just say it. A basic local sentence, right, says there exist points far apart satisfying a certain phi. The far apart requires a certain amount of quantifiers to say. In a way, they say we shouldn't count those quantifiers. And they prove us what they call a rank-preserving version of Geismann's theorem, where if you don't count those quantifiers, you don't increase the quantifier rank of the formula in going to this Geismann normal form. And then they show that there's a sort of way of amortizing this quantifier rank during this recursion, which they can bound in the process, which gets around this problem that the depth of recursion is unbounded. And the sparse neighborhood covers, I don't even have a chance to define. I mean, it's another tricky. I mean, it's a sort of nice theorem, as I said, which is a nice culmination of this line of work on sparse graphs. But I'm out of time, so I think I'll stop here. Questions?
So in the previous lecture, you had pointed out that for bounded tree width, there's a general algorithmic paradigm based on dynamic programming that allows you to kind of, take a first stab at establishing, a fixed parameter tractable algorithm for a particular problem based on bounded tree width.
Yeah.
For all of these extended forms, like let's say bounded local tree width, excluded minor, do we have of course, it's not going to be as general an algorithmic paradigm because we know of cases where it might fail, but do we have some algorithmic paradigms besides the first order stuff? I mean,
besides the first order stuff.
Well, what I mean is, first order, it's not an algorithmic paradigm. It says if you happen to be able to express the property in first order, you can do it. But an algorithmic paradigm analogous to the dynamic programming paradigm that applies.
I see. Well, I mean, there are some things. Particularly, there are sort of various things on optimization problems on, say, planar graphs, which look very much like this. You look at your bounded radius neighborhoods, and they provide sort of you're trying to optimize some function over a planar graph, and but by looking at bounded size neighborhoods, you essentially only need to look at what happens on the boundary of these things, and so on. And that can be seen as manifestations of this. But I mean, this is just a loose analogy. And I think that kind of thing extends from planar graphs to graphs embedded on any surface and so on. So it's very much starts to look like these excluded minor classes and so on. But I mean, I'm a bit out of my comfort zone here.
Just clarify. So does nowhere dense sort of...
Nowhere dense extends all of these, yes. It's at the bottom of these, extending all. So yes, so excluded minor is nowhere dense, bounded local tree width is nowhere dense. Yeah, Thomas?
What is going on right now in this area? I mean, are people trying to get beyond nowhere dense classes? And
I mean, there are interesting questions. So let me just say a few sorts of things. So these rely on sparsity. First order logic is, as far as the first order formula is concerned, it doesn't matter whether you say there is an edge or you say there's not an edge, right? I mean, so this whole argument works even if the non-edges form a sparse class, right? As far as the evaluation of the first order form. So an interesting question is, well, can you characterize the classes, right, where first order evaluation will work, where this kind of technique will work? What is the general case, right? In some sense, sparsity is not a sufficient explanation. Oh, I mean, it's not a necessary one. What else? There is a sense, there's a companion result which says, in some sense, this is a natural limit, which says that if you restrict yourself to class of graphs which are closed undertaking subgraphs, right? And first order evaluation is FPT, then it must be nowhere dense in a certain sense, okay? But the important caveat there is closed undertaking subgraphs. So if you relax that, what interesting classes can you get where first order evaluation is FPT? That's another interesting question. Okay.
But are people also trying to lower the constants used in those?
I don't know. I mean, I don't know much. I mean, the constants, I mean, those functions are horrible, and they're horrible even already at bounded tree width. As I said, they're provably non-elementary lower bounds and so on. So I don't know what there is much to be said there.
There's also the question of you have this formula that has an additional relation symbol, and you want to find the smallest relation that satisfies the formula. So it's an optimization problem, like finding.
Right. Yes.
So I understand that on bounded local tree width and on excluded
minus. Yes. Does that extend to nowhere dense?
That's the question.
Right. No, I don't know actually. Yeah. No. Did you have a question? No. Oh, sorry. Okay, I think we better stop here and start again at 11.